by Andreja Gomboc and Katja Brickman, if I'm not totally mispronounced it. They talk about tidal disruptions from stars with Rubin Observatory. Welcome to Slovenia, and please take it away.
Thank you. I hope you can hear me. Yes, so tidal disruptions occur when a star comes inside the tidal radius of a black hole and it's shredded by its tidal forces. So the basic picture goes back several decades and says that part of the material which is on bound orbits returns to the vicinity of the black hole. And if we assume simply that the mass distribution over energy is flat, we get this characteristic fallback rate for the mass T to the -5/3. And usually we also assume in this simple picture that luminosity follows the fallback rate, so it decreases with time as T to the -5/3. In reality, of course, it's more complicated, which we can also see from numerical simulations. There are plenty of different codes developed for this purpose. Some include also gravitation, general relativity, rotation of the black hole, and so on. So here we see one of those simulations. Half of the material approximately returns to the vicinity of the black hole. There are shocks produced when the stream intersects itself. Some material should also settle in the accretion disk, and there are many open questions. So we know that the X-ray luminosity is coming from the accretion disks, but the observations tell us that for UV and optical radiation, it is more difficult to tell where it is coming from, whether it is the disk, whether it is the shocks created in the self-crossing, or it is in the reprocessing layer. Observations so far detected about 90 TDE candidates. Some of them were robustly confirmed, mainly with spectroscopy. There are rare transients. Current rate estimation for current rate is 10 to the -4 per galaxy per year. And typically they rise on a time scale of month and decay with this T to the -5/3, but not all of them. So we don't have really clear photometric evidence what is the TD and not, for example, supernova, which varies on a similar time scales and also has similar peak magnitudes. What is characteristic for TDs is that they have high black body temperatures, and so they are blue, and they remain blue for months after the peak. So this is something that we also plan to use in the TD filtering, as we call it, in identification of TDs. So far, mostly spectra were important, very important for classification. So the classification was based on that. Of course, as it was mentioned already, in LSST era with so many transients, this would not be possible for all of the interesting transients. But still, TDs are very important. They can be probes for the supermassive black holes in non-active galaxies. Of course, maybe some of them may not occur in the centers of galaxies, which is an additional problem, but they can be probes of many things. So current discovery rate is about 10 per year. And of course, this is going to increase substantially in the Rubin era. So this is something that my student Katja Brickman and me were investigating. So what can we expect in the Rubin era? So we used the LSST software stack. We used operation simulator and the Minion 1016 cadence at the time. We added TDs in the catalog simulator using MOSFET. So we produced TDs in LSST bands using that. We used solar type stars, but varied black hole mass, and also the impact parameters. Stars were on a parabolic orbit. We did not exactly know which supermassive black hole mass distribution to use because of the uncertainties, especially at the low mass ends, around 10 to the 5. So we used 6 different supermassive black hole mass distributions shown here on the right, some increasing with mass and some decreasing. And we performed, we put these TDs in 20 different fields in the sky, as you see in this picture here, and simulated the LSST TD light curves as they would be observed by the LSST. Of course, there was a question that we had to solve what counts as a detection, because if we have just a couple of data points very close to the limiting magnitudes with a bad signal to noise, it is, of course, impossible to identify TD. So we arbitrarily decided that 10 observations above the cutoff magnitudes, which are limiting magnitudes -2, so this would be probably sufficient for the classification. So we see here on the right several of such simulated light curves. And the result was that depending on the distribution of supermassive black hole mass, number of detections, of course, the best distribution is the one which has a peak in the range between 10 to the 6 and 10 to the 7 solar masses for the black hole. But the main result is that using the rate of TDs 10 to the -5 per galaxy per year, we can expect 10 to 20 TDs per night. Of course, there is the question whether we will be able to identify them to trigger follow-up observations and learn more about them. We also wondered how well we could use this TD population to probe supermassive black hole mass distribution, especially at the low mass end. So here we see the results. So the purple lines are the input supermassive black hole mass distribution, and the green histograms are the output. So from this early investigation, it seems that it will not be straightforward, because the TDs produced by low mass black holes are shorter and also fainter. So it is possible that with LSST cadence, majority of them will be missed. So of course, there were also other strategies proposed, not just the one that we are using in these simulations. So we asked ourselves how this will affect TDEs observations. So we developed together with Sjord van Velzen and support from the LSST TVS science collaboration, we developed a TDE metric to see whether we can whether we can evaluate which cadence would be best. We relied on the fact that in order to tell apart TDs from supernovae, we have to rely on their color, the blue color that I mentioned earlier, which we see here that they're distinctly different than supernovae. So we developed a TD population metric, or TD SPOP metric. As the input, we use two light curves of two well-observed TDEs, one bright and long and one short and weak. We put them at 3 different redshifts with a rate of 3 TDs per night, and used OBSIM to simulate light curves. The TD, we have 3 versions of TD's POP metric according to 3 sets of criteria, the minimum sets of criteria. So pre-peak metric says that we have to have at least 2 detections before the peak in any filter. Then some color metric is more demanding. It requires 1 detection before peak, 3 detections in any filter within 10 days of the peak, and 2 detections in any filter 10 to 30 days after the peak. And the third one, some color plus U, is even more demanding, let's say, which requires 1 U-band observations within the peak and 1 U-band observations after the peak, because of this importance that we put on the blue color information. Here we see our results. So out of 1,000 TDs that we put in, the lower panel shows number of TDs that were passed through each of these metrics. So here on the top, you can see that this pre-peak metric is really not strict enough, because it lets through light curves which are quite poor, let's say. Some color is better, and of course some color plus U gives the best results, but best chances to actually that we will actually be able to identify TD, but of course the number of TDs that pass this metric is, this criteria is lower. So we estimated, depending on the cadence, There are some differences, but we can mainly say that about 2% of TDs pass this metric. So main findings were that for TDs, it is better to have a smaller footprint, so to have less TDs, but with denser sampling. And it's also better to catch them young before the peak and also to resolve the peak. So rolling cadence would be better for TDs. We also found out that if we studied that if we change U-band exposure to 50-second exposure, better. Of course, under the assumption that the number of U-band visits stays the same. Yeah, so for us, it seems that the photometric classification of good TDs would be more important than the number, just the pure number of detections. And we found out also that using more U and G band would not severely damage other science cases. So here we see that performance for U band reach, let's say, cadence for TDs is much better. While for other, this is zoom in, for other science cases, it doesn't change a lot. So we find that we can expect around 10 TDs per night. Of course, as I said, identifying them will be a challenge, and the main challenges would be how to identify TDs solely on the Rubin photometric data solely on Rubin photometric data, and of course, how to identify them before the peak, on the order of days to weeks, so to be able to better cover the peak and also trigger follow-up observations. And of course, also to measure the purity, so how many supernovae or AGNs would get through. So plans inside the TD subgroup in the TBS collaboration. Thank you. Inside the TD subgroup, we propose a dedicated TD filter, which would run on the alert stream on one or more brokers. It could also be different versions of this TD filter, and it could be developed in stages. So extracting just nuclear flares, which are coming from centers of galaxies. Of course, in this way, we may miss those that are offset from the centers. And then first, to work only on the photometric feature extractions like characteristic rise time, color evolution, and fading. And then later, when we would have a good sample, more numerous sample of TDEs, we could also go into machine learning techniques. So the data that would be required is something that would be already included in LSST alerts. So history of an object photometric light curve, astrometric data, especially galaxy cross-match and offset from the center, redshift, and also galaxy color or type, because we know that TDs prefer to some types of galaxies, but of course we should not exclude from investigation also other types. And the output would be a stream of nuclear flares with light curve features, and then also classification, including classification labels or probabilities. So this is work in progress, and of course everyone is welcome to join us. Thank you.
Thank you very much. Any questions on Zoom or locally? Yeah. Maybe I start on the cadence side. So what would be your wish cadence? Hammering every day on the same field even? Or what would be the best case scenario for you?
Well, same field would be probably too much because they are not very short transients, so they are still varying on time scale of months. So it would be smaller footprint and more U-band. That I would summarize it like that.
Yeah, thank you. Any other question, comments? Federica.
Hello, Andrea. How are you? This is Federica.
Hi. Hi, Fed.
So in my question, so given that, the Rubin strategy will be what it has to be to optimize a very complex, for a very complex landscape of transients, so likely, not to spoil any surprises, but will probably not be your ideal strategy, right? So what about ancillary observatory and observations that can be done to help you, do some of the things that we talked about, building really good training sets that would allow you to exploit more the data sets, even if they're sparser, and perhaps you don't have as many colors as you wish. Because are we still in the regime where TDEs are not so well known that we can benefit?
Did you understand the question?
Okay. There were some interruptions, but I think I get the point. Yes, so definitely more observations from other observatories would help. Of course, I would assume that this will be carried out for those transients that will be very likely classified as TDEs. Also, of course, spectroscopical confirmation would be helpful. Perhaps what we could use to our advantage are deep drilling fields. They will have more frequent, better coverage of the light curves, and also whether we can exploit those TDEs in these areas.
Thank you.
Any other question? Where's the hand up? Oh, wonderful. Oh, thank you for guiding me. Please introduce yourself.
Hi, very interesting talk. I'm Decker French. I was wondering about what you assumed for, especially those lower mass black holes in the simulation. How low do you assume you can still see a TDE? And do you assume that the rate stays constant intrinsically with the black hole mass?
So in this first set of simulations that we use different, in the second set, we just use these two observed TDEs. In the first set of simulations, we use these 6 different supermassive black hole mass distributions. The probability that a TDE would occur with this supermassive black hole mass was uniform. And then the brightness of the TDE then depends on the supermassive black hole mass. So just as the mass goes down, also the brightness of a TDE goes down. So we didn't put any cut in the luminosity of a TDE. We just put the different distributions of the mass of the black hole.
Great. Any other question, comments on Zoom? No one? Well, then let's thank speaker again. Great.
Thank you.
And we will reconvene at 2 p.m.